Okay, thank you very much, Professor Suen. So let us begin today's sessions with our plenary speaker, Professor Umapada from Indian Statistical Institute in Kolkata, India. He's a very accomplished researcher, published more than 400 research papers in the area of pattern recognition and computer vision. He's also chief co-editor-in-chief of Springer Nature Computer Science Journal and many other journals. So without further ado, please, Professor Umapada, please start your presentation.
So thank you, Adam. I don't know, maybe we will have to say good morning for Montreal, good afternoon for India, and also for that Hong Kong is good evening. Okay, so today I am planning to give a brief note on air writing recognition without depth sensor. So that means you don't need any depth sensor. That means without depth sensor, how you can recognize the air writing. But what is air writing? So air writing means, for example, you have a mobile, right? So when you send something to your friends or some SMS or email, so generally we type here, right? In your mobile, so a small keypad is there, you type and then send. So instead of writing in your mobile or maybe typing on the keyboard, is it possible you just write in the air? So if you write in the air, then we can develop a system that whatever you are writing, automatically it will be recognized and then it will be stored as a text file and you can send it by email or SMS, whatever you write, right? So this talk is related to air writing. That means how computer can recognize the writing which are done by hand or maybe some other device and without touching anything. It is in the air. That means you are writing in the air. Okay. So for example, I'm just showing you one small things here. You can see this is one demonstration of our system, what we have developed for India. So my student is writing in the air. And you can see he is writing, it is an English system, he is writing 0 and it is recognized as 0, right? So he is writing 2, it is recognized as 2. So similarly, it is 8 and you can see in the left side, it is recognized as 8, okay? So the idea is, whatever you will write, automatically it will store and then it will help you not to type anything from your, with your mobile or your desktop or laptop, anything, okay? So what is air writing? So air writing, so are you getting my slide properly? Or there is no obstacle, right? I hope you are getting my slide.
It's okay, yes.
It's okay? Okay, thank you very much, Adam. Okay, so air writing is, maybe I'll just take some figure outside so that I can, it is, yes. Okay, so air writing is, it is a generic video camera based air writing system that will be very useful because if you have a, now we have the mobile, we have the laptop, everything, right? So what we can do, we can write whatever you want in the air, then automatically it will be recognized, okay? So yeah, what is air writing? So air writing refers to virtually writing linguistic character through hand gesture. That means what you can do, you just move your hand. So then based on the hand movement, system can identify what you have written in your 3-dimensional space, okay? But there are earlier systems that is based on Keynote, lip motion, arm band, etc. So maybe on finger band also. So people use some sensor and that sensor will work as soon as you will move your hand. But here our idea is not to use any sensor. Your mobile camera or your laptop camera will be enough for detecting the writing what you are doing based on your hand gesture, okay? So actually, since the Keynote and Live Motion, these are not widely available, and also you have to pay some money. So we are not using any device for this. So we'll just use our hand gesture for this recognition. Okay, so this is basically the introduction for the AR writing. And here our idea is not any, that means we do not use any external depth or motion sensor. So we just use laptop or mobile camera. Okay, so no need of any external devices for this. Only your existing camera is enough for us. Okay, and here we have some demonstration for English. Maybe we will show you something for demonstration for Bangla. Okay, you can see here. So maybe here you can see. So my student is writing in Bangla some character, but 0 is common. This is 1, and now it is recognized as like this. It is 1. It is 2 in Bangla, and this is recognized as 2. This is 3, and so on. Similarly, if we want to see some Hindi character, then we can see here. So my student is writing the other Indian language, Hindi. This is most popular language here, and he has it in the character. Yes, this is 3. So something like that. You can have all this information. So you can see once more. This is for Bangla. If they can write like this. But here the student is writing only single character, right? Single numeral, not character event. So numeral. But what happens when we will have sequence of numeral, right? Okay. So we'll just go back. So why we're doing this work? So what is the application? So as I mentioned you, so one application is the mobile application. That means no need to type through your keyboard to send email or SMS. That means, for example, in a small kid, so every day nowadays you can see the kids are always using this mobile. So if he or she uses his mobile or her mobile for a long time, maybe it will be bad effect for his or her eyes, right? So that means AR writing system is good for eyes, for your eye, let's say. Similarly, that means it is touching independent. That means you don't have to touch any common public sensor, right? So you can write in the air. So that means you can do your air signature, you can write whatever you want without touching any public sensor. So other application is, so you know the deaf and dumb people, they cannot speak, right? Or they cannot hear. So they have their own language called sign language. So we can use this system for the sign language recognition also. So how we can do that? Actually, the deaf and dumb people, they use some symbol, that is their hand movement, and also their facial expression. So here, our idea is use of facial expression and also this AR writing technique for this hand movement to communicate the normal people with the deaf and dumb people. So that is another application of this AR writing. Similarly, we can say the other application is like a medical application. So for example, in an operation theater, that means OT, a doctor is there. And doctor wants to take the notes of his or her patient. So for example, he is in the OT and he wants to take the maybe some figure of his heart, how it is working or something. So what he can do, doctor has gloves and maybe knife in or his or her hands. So she or he cannot write. So what he can do, just she or he can do something like this, and based on that, everything will be stored in your system. Okay. So this is the medical application. So that's why we have recently started that AR writing without any sensor. Okay. So what is the difference between AR writing and the online writing recognition? So you know, for online writing, for example, when you have a paper and we are writing something, we use pen up and pen down. That means pen down means we are starting and pen up means we are the ending of the writing, right? So in online, we know that pen up and pen down information, and that information can help that where you have started writing and where you are stopping writing, right? That means you can have the stroke information or character information based on the online pen up and pen down information. But in air writing, when you are started writing, you don't know where you are starting and where you are stopping. So that is the most important things for the air writing. So there is no pen up and pen down information, and hence we do not have any stroke information. We don't know where is the starting of a character. I'm just moving my hand like this, right? So how to get this information? This is a very interesting research issue and also very important research issue, and we need to take care of that. Okay, that means whatever I am writing, where is the end, where is the start, and what we have written, that we have to recognize. Okay, so what are the problems then we are facing? Actually, you know, due to the high variability of human skin tone, that means the color of the skin, it is very difficult to segment the hand or finger from the background, what you have there in your background by the color segmentation technique, right? So, but we have started some work, and one of my students is working now to segment the finger, and based on the fingertip, we can know what he has written. Okay. But for that, what we need to do, we have to segment the hands, but it is there already, segmentation of hand. There are some work in CBPR. And also we have to segment the finger, and you have to find the tip of the finger, and based on the tip, we can know what you have written, right? So to make it easier, what we have done here, so maybe you can see these things. So you can see what we are trying to say, that we'll show our system. Let's say I am using this pen for my writing. So my student is showing different pen. Can you see here? He's using different pen, and now he is getting the pen information here. Okay. So maybe I'll just show you once more here. You can see the people, my student is using two different pen, and just he is showing this pen to the system. Okay. So he is asking, okay, this system, okay, I will use my pen. So take the information of this pen so that I can use this pen for my writing instead of the finger. So he is doing the same thing here. Can you see here? He is just showing the system to the pen. So there is a point. He is just keeping the pen on that point, and then automatically the information is stored. He is taking another pen. He is just saying here. Now you can see he is moving the pen, and we will get the pen information. Okay. So that's why, what is our aim? So we are currently working on finger-based system for air writing. But to reduce the complexity of the multicolor skin segmentation, because different people has different skin color, so we show an user the skin of the system. So let's say I am showing my skin to the system, and then system will take the skin of mine, and based on that we can do that. Similarly, we can show not only the finger, we can use also some sort of pen. Let's say here you can see, as I shown you earlier. So this student is showing a pen to the system. You can see here, he's showing the system now, and now you are getting the pen information, and we can use that pen for writing. Similarly, he is using another pen here, and then he is getting the pen information. Now he can use this pen. He can use any of the pen. It doesn't matter. Okay. And also we can use the finger also. But we already developed the system for finger. But the problem of the finger is when the finger is coming to the face, then it is confusing the finger and face. So this problem we are solving now. Otherwise, we can use the finger for this writing. Okay. So so what is our aim here? Our aim is you just write in the air, and whatever you will write, it will be stored. Okay. Then what are the problem? Problem is how computer can know where is your starting and where is your end for the writing, right? So what we have written. So for that, we just developed a system, and we'll just discuss those systems to you so that you can get the idea, and that idea can be used for developing system for different languages, because it is language independent. Okay. The work is, so what we have to do, so we divide into two stages. One is motion tracking. That means you have to, whenever you are writing, your hand is moving. So how you will get, or how will track your hand, or how will track your writing device, and then we'll just go for recognition. So these are the two tasks we have to do here. Okay. So here you can see my student is using a pen like this, and you can see whatever he is moving the pen, we are getting the pen information. And then if you take the top of this pen, and then we can know what are the points we have moved during writing, and that points, that means those set of points are the input for our system. That means that is the coordinate, like online writing coordinates, and we can get the coordinate, and based on that coordinate, we can get the information about the writing. So here, a color-based segmentation technique is used to generate a marks, like he is using a pen and he is getting this information here for a desired color or different pen, or maybe your finger or something else, and you can use that information for the writing. Okay. So first thing is you have to find the marker tip estimation. That means whatever, when you are writing something, how to get this information. So as soon as we can get this marks, you can see we can get the marks, and then you can take the top of the marks, and that top point of the marks will be the points for our input. Okay, I hope it is clear for you. That means what is the input for us? The input is, that means movement of my hand. That means movement of the fingertip. If I use my finger, if I use my pen, then the input is that top point of this pen, whatever I am writing, so that coordinates of the top point will be the input for it. Okay. Yeah. So then what we will do, so we will just take the topmost point of that contour of that boundary, that means this boundary, and then the sequential set of positional coordinates of the marker tip, and that will serve as the input of our system. Okay. So this is basically the important information for us. And then when we will terminate. So for example, when you are writing, so maybe if your writing is out of focus of your camera, that means we are assuming that it is the end of your writing. Or maybe when you are writing and you just don't move your hand, then we can say this is also end. So these are the 2 points we consider. Where is the stop? That means when your finger is out of focus or your finger is stopped, then we can know that this is the stop criteria. That means whatever you written, it is a set of input for you, and you have to go for recognition. Then again you can start like this. Okay. So this is the termination condition. As I mentioned you, these are the 2 conditions we are using for terminating things. And now you can see that whatever we are writing here, so as you know, he is writing now touching character 360. So that means he has started and then he has moved like 360 and then he stopped, or maybe it is out of focus, right? And now we have to recognize what he has written. So for our system, it doesn't matter whether you are writing a single character or single numeral, whether you are writing a 2 character or 2 numeral or many numeral at a time. So you can see here, he has written 3 numerals at a time, 360. Okay. And later you can see what is the output for this, right? Okay. Okay. So as I mentioned you, the problem of the air writing and online is different, because in online you have the pen up and pen down. But here, you don't have that one, right? And also, you will have some extra information. So, for example, when we write in the pen up in online, we just write 7, and then we'll just take the pen up. Then again, we'll start 9, and as soon as 9 will be completed, again the pen will be up, and then we'll pen down and write 5, 7, 9, 5, something like that. But when you are writing in the air, so my hand is moving 7, and then 9, then 5, right? So that means you can see here, after writing 7, you can see, maybe you can see my mouse perhaps, then you can see here that 7, then the red part is the extra part is coming due to my hand, because my hand cannot stop and pen up and pen down. We cannot use that. So hand is moving, we are getting the image. So when we write 7, that means 7, then again it is going up, that is the red part, and then we starting the 9, right? So we have some extra strokes due to the air writing. So that is the problem, and how to remove those ones, right? So main problem of air writing is how to know the start and end points of a numeral or character or word. So if your input is only a single character, it is not a big problem for you. But when you are writing multi-character or multi-digit, then problem comes for the continuous string, like 7, 9, 5. So the red part is red and the green one. So red part for the after 7 is extra. So this green one after 9 is extra. And again the red part after 5 is extra, right? So these are the extra part we will get. Similarly 3, 7, 9 we will also get some extra part, right? So what we can do actually, so in this case, we can develop system in 2 ways. One simplest idea is you just segment this continuous writing into stroke. So what is stroke? We know everybody. So everyone knows what is stroke. That means when there is a sharp change of angle, we can say this is the end of a stroke. So we can segment based on the stroke information. That means the curvature information of the writing. We can segment the strokes. So that means every numeral can be considered as a set of strokes like this. You can see here for 3, we can have first strokes in the right side, the red one and the green one. Similarly for the 4, we can have 3 strokes, red, then middle one and also the blue one. So we can segment the strokes and then we can consider these strokes as the unit for us. And then what we can do, we can use this strokes information to develop the different characters or numerals. So if we know that okay, 3 is actually developed by these 2 types of strokes, then if we can recognize what are the different strokes we are getting, then we can easily recognize that this is 3 based on the stroke. Okay. So idea is what we are doing. So for continuous air writing, we will consider here numeral string recognition for this discussion. So how to know the start and end of a string of numerals? So can you use any language model for this? But we cannot use because the numerals, they don't have any language model, right? So to incorporate language model, what we can do, so we can segment the writing into strokes and then we can propose some stroke language model. That means how the strokes develop numerals, and that can be considered a language model for us. Okay? So that is the idea, one of the approach. We can segment into strokes and then we can recognize stroke, every stroke, and then we can develop the grammar based on the positional information or the recognition result of the strokes. That means we can use stroke language model for the recognition. Another approach is you don't have to segment the strokes. So whenever you start from here, so you just try to recognize. As soon as we are getting some recognition result, we will say this character is this one. Again, we will start from there and to recognize another one. So we will recognize character by character, one by one. But then how we can know which character is written. For example, if we want to write 3, maybe when we write 3, it may comes 0, then it comes like 2, and then 3. So that means to write 3, we may have 0, 2, and then 3. So how we'll overcome those things? So that is a very interesting idea, that how we can recognize directly 3 instead of going to 0, 2, 3. I will come to that part later. Okay. So we have developed a actually based on the information of the different language. So we have a priority scheme. That priority scheme can be used for doing that. I will come to that part later now. Okay. So this is one approach for a stroke-based model. And then we can recognize the stroke-based model and then develop the grammar and recognize that one, right? So another one is what we can do. We recognize the 10 digit because we are considering now digit. And then after digit recognition, we'll use some prediction pool. That means we have information about the prediction of different numerals. And based on the prediction pool, that is based on the probability of the occurrence of character followed by another character or numeral, and we will predict which character it should be. Okay, and based on that, we will recognize the what you have written. Okay, so this is the overview of the system. So as I mentioned you, once you have written, then we will get what we will get. We will get the coordinate of the finger tips, right? So that is the coordinate. That means point number 0, this is the coordinate xy. Next one, 26, 129, next one. So we have a set of coordinates. So that set of coordinate is the input, as I mentioned earlier. And that input, we can feed this input to our classifier. So we use a different classifier, and based on the classifier, we can recognize. Okay. But as I mentioned you, when you are writing, let's say 3, you may recognize 3 as 0, 2 before recognize 3. Okay, I'm coming to that part. So for example, if I want to show you that one, let me check. You can see here, this one, this is a 3, right? So first part, which is marked as red, this is the first part of 3, and this may be recognized as 0. Then the red one, and after that the blue one, so first red and then blue, that means up to this, it may be recognized as 2. And then if you consider all this red, blue, and again red, then it will be 3. That means while you are writing 3, our system may recognize total points as 0, then 2, and then 3. So to use this information, we have a priority scheme. So maybe I'll just show you one. You can see here, it is up to 0. So then it is 2, and then it is coming as 3. So that means to write 3, we are coming to 0, then 2, and then 3. Okay. So maybe I'll come back to this one later. So before that, I will just quickly tell you what is happening. You can see we are just starting from the first point, and then we are getting, these are the different enhancement of the points. That means the sequence of the points. And then you can see as soon as we are here in the 5th column, then a 4th column, then let's say, and then we are getting, this is a numeral 3, and we marked as the different bounding box. Okay. And then again, we are considering what is the next one. So as soon as we will be recognized as a particular digit, then we will start from this coordinate to recognize another one. Okay. So in this way, the process will proceed. That means as soon as like this, the 0, then from after 0, we are just see what is happening, and then what is happening, we will go in this way. Okay. And then for the recognition, we use our network. So that means we use 2 network, that is RNN and LSTM network, and for the recognition. And based on the results, so let's see. So we are okay. So Adam, how much time we can get?
I think it's about 10 minutes, I would say.
Okay, thank you very much. I'll try to summarize in 10 minutes. Okay, so this is the network. So I'll not give you the details about network because we don't have enough time. But after the recognition results of the network, before that we use a different data set. So data sets, we use both the online data set and the offline data set. And for offline data set, we use the MNIST data. And for online, we use the PenDigit data. And also, we have developed our own data set for AR writing. So that is that ISI AR we call. And that is available for the other people if somebody wants. So you can write and we will be happy to give you the data set. So this is an online AR writing data set that is for English numeral. And also we are using some other noisy data set. So that is also AR writing data set. We develop those things. So we are using this data set for our training, and based on the training, we will go for recognition. Okay. As I mentioned you, so we need to use some prediction pool or prediction theory to know which characters is coming before other character. That means, let's say, if we consider numeral, so when we are writing or recognizing 3, maybe we can have 0, 2, and 3. So based on this occurrence statistics, we made a prediction pool, and based on the prediction pool, we'll develop our system. So we have, so after being passed to the network, the predicted values of all the frames are stored in an array, which is referred to the prediction pool. And then prediction pool is sent to the priority scheme, which determines the correct value out of the pool of values, and then we'll recognize that particular set of points to the particular digit accordingly. Okay. So as I mentioned here, when you will write 3, you can have 0, then 2, and then 3. That means before coming 3, you may have 0, you may have 2, you may have 3. Then how will overcome? How will not say it is not 0, 2, 3? Okay. That's why we need the priority scheme. And that priority scheme is based on the, it is a two-dimensional matrix. So priority matrix, we call it is a priority matrix. And that priority matrix is a n cross n matrix where n is the number of classes. So for example, if you consider digit, then n is 10 because we have 10 digits. So which detects, so it detects that transition between which class are possible. That means when we are coming to 3, which are the possible class we may cross. That means when we will come to class 3, we may cross class 0, class 2, and then 3. Okay, so that's why we develop this based on the statistical model. So priority matrix is created passing to the handwritten dataset for what is the problem for that network problem? I think it is okay. So we use that different sets. We will have different priority matrix. So for example, Bangla numeral, we will have the different priority matrix than English numeral or Hindi numeral. Okay. So for each language, we need this priority matrix because the shape of the characters is different. Okay. But the technique is same for all. So this is basically the priority function. So priority function has 3 values. One is 0. You can see this matrix, 10 cross 10 matrix, and the values of this matrix is 0, -1, and 1. So what is the meaning of 0? So 0 means when the 0 is recognized as 0. That means the 2 input. So x. So the priority matrix can have 3 values, as I mentioned, 0, positive, +1, and -1. So f of x, y, that means a function, that means a transition from x to y is possible or not to predict y. Okay. That means you can see here in the first column of this matrix, for the 0, we have the positive one for 2, 3, 5, 6, 8, and 9. That means when you write 2, 3, 5, 6, 8, and 9, then we may have 0 before recognizing this character. Okay. So similarly, you can see for 0, we have 0. That means 0 will be recognized as 0. And when you write 1, you cannot get 0. That's why it is -1. So -1 is, there is no possibility of getting a transition to get 0 to 1. And +1 means we can have a transition. So that's why we have created this priority matrix, and based on that, we can know which numeral or character we have written. Okay. So now you can see here. So the character is actually 3, but before coming there, you can see we have the 0, we have 2 and 3. So, and we know when we will write, if we have 0, 2 and 3, that means it may 3. That's why we detected that this character is 3, because we have the prediction pool 0, 2, 3 for 3. That's why the actual prediction is 3. Similarly, we can have the prediction for each of the character in different way. So the final prediction will be done based on this priority scheme. Okay. So similarly, we can have a different character like 6 and 8. You can see when you are writing 8, we can have 6. Okay. So 6 and 8, which will come to 8. And here is the actual demonstration of the system. You can see here, my student is writing some character, let's say 2. And you can see in the left side, it is the recognition result. And this is the predicted values as 2. You can see the predicted result. Now he has written 3, 6. This is the image of 3, 6, what we have written. And this is the predicted values. And he has written 2, 9, 3. Then in the left side, the image will come as 2, 9, 3. And then after prediction, the prediction value will be 293. Okay, maybe I'll just repeat the same thing once more so that you can understand. He is writing in the year, that is 2, and the prediction value is 2. Now he is writing some 2-digit character 36, and now the prediction value is 36. You can see here, this is the prediction value. And now here 3-digit number 293, and the recognition result is 293. But you can write not only 293, you can write maybe 4-digit, 5-digit, but because of the scheme, we have written only 3-digit here. Okay. So to get the accuracy, so we have tested the data for different data set, and our system at present is giving 98.45 for single-digit character, and that is based on MNIST data set. And also for the multi-digit characters, we are getting the results like this. When you have digit count is 2, that means you are writing 2 characters at a time. The recognition is 84. And when that is the forward scan. When you are writing 3-digit character, recognition rate is reducing. It is 73. When you are writing 4 characters at a time, it is less. It is 64. So to improve the results, you can see in the third column, it is the forward scan accuracy. So what is meaning of the forward scan? That means when you are writing, you are starting from here and going like this. What we did, we use this forward scan. That means starting from the first pixel, we just take the set of points or pixel as the input. Similarly, we took the last pixel and we took set of the previous pixel from the start end point to last point, then first point. We are just going back. That is the backward scan accuracy. So we use this backward system and also forward system. So we have 2 systems. The image one is for forward scan and another set of point is the backward scanning. But the same thing we are doing here, only 2 different data sets we are using, forward scanning and backward scanning. And we merge these 2 forward and backward to improve the result. That is called bidirectional scan accuracy. and we got much higher recognition. You can see earlier for 2-digit recognition, this one, we got 84%, and for bidirectional, we are getting 97%. It's more than 10% accuracy, higher than that one mode. So that means we are using 2 modes, forward mode and the backward mode. Okay. So, and that help us to remove some of the confusion to get the proper result for this bidirectional scanning. Okay. So this is the current state of the results. And there are some papers, but most of the papers, as I mentioned, they are using some sensor. Okay. Either they are using Keynote or some other armband or some other sensors. Okay. But here we don't use any sensor. We just use your mobile or maybe laptop camera, and that is enough for your writing. You just use like this. Okay. So this is some of the reference for you. So we published a recent paper, and that is Asian confirmation pattern recognition. And also there is a paper in IEEE multimedia that is for air writing, but they are using Keynote sensor. So people are using some sensor, but here our aim is not to use any sensor. So to conclude, so we propose a robust hardware independent. That means we don't need any device, external device. So hardware independent framework for multi-digit unistroke air writing numeral recognition. So why unistroke? Because you are just writing like this. You are not stopping somewhere. So your stroke is 1, but it is combination of several numeral or characters. Okay. So even though the test is performed that English, but the methodology is language independent. Only thing is you have to develop that matrix accordingly. And as I mentioned you from the experiment, we are getting about 82%. And when you are using that both directions, then we are getting about 97%. So as I mentioned earlier, we have developed a system data set that ISI AR, which is a custom online AR written, handwritten English numeral recognition. So this data set will be free available for the research purpose. So with this, thank you, Professor Suen and the entire team for inviting me to give this information to you. And thanks to Adam for chairing this session. And I'll be glad to give you the answer if you have any question. So thank you very much.
Thank you very much, Professor Pal, for your nice presentation. And now we are waiting for questions. Any questions to the speaker?
Yes, sure. So how we can get the question? Participant can ask directly, or it will be given to you and you will ask me?
There is a up here or a link, questions and answers. And yes, I got a question here, so I can read it to you, or maybe you can see it. Can this system be extended to multi-stroke characters like IJ and so on in the future?
Sorry, could you, Adam, can you please repeat? How I can see that? I can see the question, right?
You can see the question.
Yeah, I got it. Can this system be extended to multi-stroke character like I, J, etc. in the future? Yes, that is a very good question. In fact, it is a very difficult question for the air writing, because so when we write I, so what we are doing basically? So I means we have to write this and then again go there and stop this one. Okay, so then again you are coming here. So that we need to use the positional information for this character. Okay, that means how your characters, that means how your hand is moving to recognize this. So I and J, not only that, when you have some the dots at the top or the bottom, something like that, so you have to use this positional information. So thank you. It is a very nice question. In fact, I didn't discuss these things in this talk. Is it okay for the question? Is it? Are you happy? I don't know who has. This is Puneet, right? Puneet, yes. Puneet?
Puneet, yeah.
Thank you very much, Puneet. Yeah. So.
You mentioned MNIST, that you trained this your system on MNIST, but MNIST is a handwritten database, is not error characters. They are handwritten database. Does there exist a version of MNIST for error writing, or you?
No. That is the offline data set, because MNIST is not the error writing data set.
Exactly.
So we use this offline data for our training. That is for training purpose, not the testing.
Okay. So you train on offline
data
and you test it and error.
Yeah, we train offline because we don't have enough data for the error writing. So that's why we use the different data set for the test for the training.
Okay.
Yeah. Thank you, Adam.
Thank you very much. Thank you. So I think there are no more questions, right? So we can end the presentation. Thank you very much. Congratulations.
Okay. Thank you very much. Thank you. Thank you, Professor Suen. Okay.
So now I think we'll be moving to the next, to the oral presentations, correct?
Yes.
Yes, sure.
And the first one is given by Elham Vahdati and Professor Suen, entitled Facial Beauty Prediction Using Transfer Learning and Multitask Learning Techniques.
Hello everyone. Our paper title is Facial Beauty Prediction Using Transfer and Multitask Learning Techniques. The importance of facial beauty has become more evident in recent years, and people pay greater attention to facial beauty. People usually spend a considerable amount of money and time on aesthetic plastic surgeries and cosmetic products to have more attractive faces. The secrets of facial beauty have attracted the attention of researchers from several fields, such as computer science, human science, and medicine. The objective of facial beauty prediction is to develop a human-like model that automatically evaluates facial attractiveness. Automatic analysis of facial beauty has many interesting applications. Some are related to facial image beautification, aesthetic plastic surgery planning, cosmetic advertising, and recommendation systems in social networks. There are three major steps for facial beauty assessment. In the first step, a set of face images are collected, and human raters are asked to rate these faces with integer numbers. For example, for a 5-point scale, 1 is the lowest score and 5 is the highest score, and then we compute the average of these ratings as our ground truth. In the next step, data which are pertinent to attractiveness are extracted from face images, and at the end, an automatic rater is constructed using these data. Facial beauty prediction methods fall into two groups, two categories, traditional methods as well as deep learning-based methods. In traditional methods, handcrafted features such as geometric, texture, color, and shallow predictors are used, but recently, deep learning techniques, especially CNNs, have gained in popularity, and they have boosted the performance of facial beauty prediction methods. Because hierarchical and high-level features of face images are automatically extracted using these techniques, but publicly available face data sets for our task are not extensive, and I mean our training data are not extensive. So in order to alleviate this data insufficiency problem, we decided to use a deep CNN pre-trained on millions of face images. In fact, we reduce the difference between the source task and the target task in transfer learning scheme. More specifically, we use the ResNet with 50 layers, which has been trained on 2 different face datasets. MS-1M face dataset with 10 million face images, and VGG phase 2 with 3.31 million face images. Also motivated by the human aesthetic perception mechanism, where the beauty assessment standards differ for males and females. We use a multitask learning scheme to jointly perform gender recognition and facial beauty prediction tasks. And this multitask learning scheme enables us to extend our model to another face attribute, face ethnicity. And our model uses a multitask learning scheme to learn optimal shared features for these correlated tasks. This is the first attempt work to employ a very deep network pre-trained on millions of face images for facial beauty prediction task. And also, this is the first work where both transfer and multitask learning techniques are employed to investigate how beauty score prediction as a reversion problem and gender and ethnicity identification tasks as classification problems can be combined together to enhance the accuracy of attractiveness prediction. Our proposed network is composed of 2 main steps, shared feature extraction as well as multitask estimation stage. By fitting face images to a pre-trained ResNet on millions of face images, built upon average pooling layer, we have 3 branches for beauty, for gender, as well as ethnicity. Beauty score is a real value between 1 and 5. So we use the mean squared error loss function for beauty task. Both gender and ethnicity identification tasks are classification, and we use the cross entropy loss functions. And then we use the weighted sum of these 3 individual losses. And the weight parameter lambda is determined based on the importance of the task in the total loss. Because facial beauty task is our main task, we assign a higher weight to facial beauty task. Also, we use the Scott FBP 5500 dataset. This is a publicly available dataset, and it includes 5,500 face images of both genders and different races, Asian and Caucasian. You can see some examples of these example faces of this data set here. We use in our experiments, we use the 3 metrics, Pearson correlation, mean absolute error, and root mean squared error, and also we use 5-fold cross validation. And we reported the average of these 5 folds here. You can see beauty is our baseline beauty task, and you can see by adding more face attributes, we achieved a higher Pearson correlation and lower errors. And also we compared our results with the results of other methods, and our method outperforms others. The main reason is that our method gains benefit from transfer learning methodology as well as multitask learning scheme. And good initialization derived from a very deep CNN on millions of face images, as well as leveraging the optimal shared information among related tasks, make our method successful. And also, multitask learning scheme enable us to extend our model to other face attributes which have a significant influence on attractiveness of a face, such as trustworthiness or even non-permanent features such as makeup. And thank you for your attention.
Thank you. Thank you very much for your presentation. Are there any questions? Maybe let me just ask you one question. What kind of database do you use for training your system? Are there benchmark databases for?
Yes, I use the Scott FPP 5500 face data set. Is publicly available. It includes the 5,500 face images, and the others of that space paper who released this data set, they splitted this data set into 5 folds, and I am using the same folds, and I reported the average, and also I compared my results with their work. You can see here these 3 deep networks are from that paper, and you can see my results are better. I have a higher accuracy than their work.
Who annotates the system? In other words, who decides that a person is beautiful or not?
For each face, 60 human raters are asked to rate these face images, and then we calculate the average of these ratings as our ground truth. Okay. 60, yeah. These data sets have been rated using 60 labor human raters.
And the sense of beauty may differ across the different cultures and races and countries and so on, I suppose, yeah?
Experimental results shows that even people from different ethnic backgrounds share similar taste and means when rating the beauty, and it's not completely subjective, and it's very interesting. Even new infants gaze at beautiful faces. No, it's not. I mean, it's not completely subjective, because some papers showed that people from different ethnic backgrounds share the similar criteria when assessing the beauty.
Okay, thank you very much. I think the time is up, so we have to move to the next presentation.
Thank you.
Again, thank you for a nice presentation.
Thank you. Bye.
Okay, so here it is. Mohamed Chelali will present the next paper entitled Spatio-temporal Stability Analysis in Satellite Image Time Series. Please go ahead.
Hello everyone. Today I will present you our studies entitled Spatio-temporal Stability Analysis in Satellite Image Time Series. And based on the title, we see that our context is about the analysis of satellite image time series. As we see in this figure, this is the data of our study. And these large quantities of data allow us the analysis of the evolution of our planet. And some thematic usage of SITS is the mapping of our land use and also manage our territories. And as we see here, each pixel represents a time series that allow us to analyze the growing of the area. And as we see here, these pixels is taken in 2 different regions, and each one has its self-evolution. But the goal here is how to differentiate between these two kind of pixels to label them if they are in agricultural or urban area. And the problem here is the analysis of change on the temporal evolution. And as we see here, based on this evolution, is this pixels in an agricultural area or a urban one? And how to deal with the spatial and temporal information at the same time. As we see here, these pixels, this time series represent the pixels in the middle of this crop. How to include the spatial information for this time series. Some existing methods for seeds analysis are different. They are that consider the pixels as a set of time series and use random forest or K-means to classify them. Others propose the dynamic time warping, which is a distance that allows us to analyze the temporal alignment between the time series. And this kind of distance can be coupled with the K-means or KNN. There are also recurrence plots, where this method starts by transforming the time series into 2D images. Then by using 2D classical CNN, we can classify them. Some deep neural network methods, as the most known is the LSTM, which is a kind of recurrent neural network. And also we find the time CNN, which is represented here. And this time CNN applies the convolution only on the temporal domain. Some research that includes the spatial information extract some handcrafted features computed at a region level. As we see in the figure C, these features can be morphological, geometrical, or colorimetrical. And then these handcrafted features are associated with their initial time series after we use the K-means or random forest to classify this enriched time series. Some hybrid strategies use a combination of two different neural networks. For example, we can use the 2D CNN to learn spatial features, and in other side we use 1D CNN to learn temporal features, and after that we can merge these learned features in order to use spatio-temporal features. And some method to analyze a sequence of images, we find a 3D Hawk, which is a histogram of gradient, which generally used for video classification or action classification. And we found also 3D CNN, but with these models, we require large quantities of database in order to fix all the parameters. We pass now to our proposed method. We remind that our objective is the characterization of change. For this, we hypothesize that urban area do not evolve significantly through time compared to natural area. As we see in this figure, the bottom pixel is on urban area and the top pixel is on natural area. We see that the natural pixels are affected by some evolution through time. So instead, by looking change, we are going to study the stability, which is where we see it in urban area, which is a more stable pixel. For this, we are going to use the random encoding algorithm, which is based on the repetition of successive values. And we apply this algorithm on each temporal pixel. And based on the compressed code, we are going to extract the max stability, which is here 2, because it's the most repeated one, and we extract 6. We can also extract the max stability start, which is the index of where the max stability start. Here it is the sum of 4 and 3. And we can also extract the number of change, which is here 3, because we have 3 transitions between the the stability ranges. But the notion of equality is the cornerstone of the stability. Why? Because we see that in the original time series, we have a high variability of values. And the comparison between colored pixels are complex. For this, we are going to apply a quantization of the values of the whole of static image time series. We do this by applying a k-means with a k-quantize being the parameter of the method. And by applying this quantization, we can compare two successive values with their quantified values obtained by the k-means. As we see in this figure, the original time series is continuous through time, and with their quantization, we can easily extract defined features before. And the same thing for the pixel in the agricultural area. Else now, we extract our features by strict equality between the values. But in the reality of data, we can find some outliers, or we can find also undetected clouds. For this, we are going to relax the equality on the temporal domain by skipping some values in order to escape for this problem. We can also relax the equality on the spatial domain by comparing pixel at time t with its neighbor in the next image. And we can also combine both of relaxation on the spatial and the temporal domain. We note that the first features are only temporal, but for the two last features are spatio-temporal because we include some spatial information. We pass now to our experimental study. The used data are satellite image time series provided by Sentinel-2 satellite since in 2017. Two cities are selected for this studies. We note that we apply the linear interpolation on masked zone by clouds in order to fill all the missed values. The used reference data are the imperviousness product, which it represent the percentage of soil sealing. But in our case, we consider only two classes, the artificialist one and the natural one. And for the experimentation, we use the vegetation index, which is the NDVI computed by this formula, and the quantization applied here is done with the k equal to 4. We see here the used classifier are in our classification problem are the decision tree, random forest, and some CNN. The used features are the original time series and the mean of the time series and our features. The used classifier depends on the length or number of used features. For the first experimentation, we are going to train on Mulhouse City and we are going to test on Strasbourg City. We see that when we use the mean of the time series, we do not obtain a good visual result. But when we use only our features in the spatio-temporal domain, we have a better result. And by combining our features with the original time series, we see that the obtained visual results are better, and it is almost the same compared to the ground truth. For the quantitative result, we see that with the mean of the time series, the score is the worst one, which is normal. And by using only a decision tree with our spatio-temporal domain, we have 80%, 84, 85% of accuracy. And by combining our spatio-temporal features with the original time series, we see that we obtain the better scores. And we perform a deep neural network method. To conclude, we present here in our studies spatio-temporal stability features that it is used to classify image time series. And in our perspective, we are going to analyze finally the notion of equality by extending the kernel size when relaxation is applied on spatial domain, and how we are going to compare two colored pixels, and we will try to apply the method on the other kind of image time series. Thank you for your attention.
Thank you for your presentation. Any questions? Okay, so I would like to ask the following question. You indicated on slide 6, one of the last, yes, exactly, on this slide with the next one, yes, next one with result 7, I think. Slide 7 with the results, with the table, yes, this one, yeah, computational table. Your results presented in the last two rows are slightly better than deep networks, right? And
yes,
here,
is
there a significant difference, or they're just slightly better? And could you claim that they are that your method is definitely better, or it's compatible to benchmark methods?
Are slightly better, and we see that it depends also on the training set, because when we train on for example on Strasbourg, we see that we have some region in red color figured on natural area. So for this, the obtained result will be misclassified. But when, for example, we see that when we train, for example, on Mulhouse, we have a significant difference between scores.
Right. Okay, so thank you very much for your presentation.
Hi everyone, I'm Zhenyue Zhu from East China Normal University. Today I want to talk about object detection based on sparse representation of foreground. First of all, I will introduce the background of object detection on X-ray images. As a huge number of baggage needs to be inspected, it's desirable to fulfill this inspection automatically. The realization of automatic detection can not only reduce the workload of human inspectors, but also increase the inspection speed. In recent years, more and more scientists paid attention to automatic image recognition for security inspection. Some researchers generated a visual codebook to classify the image features and then detect treat objects with the use of support vector machine. Others proposed a model to classify the query images by voting the selected patches which had been classified by sparse representation classification with an adapted dictionary. Meanwhile, some methods use a pattern convolutional neural networks with transfer learning to classify the X-ray images. Our approach was a revision based on the paper proposed by Mary D. that a logarithmic X-ray image model for baggage inspection. In Mary's work, a testing image could be modeled by the sum of the contributions of the foreground and the background. So detection of the treat objects could be achieved by analyzing the contribution of the foreground and the background dictionaries. Foreground dictionary was obtained from the patches of the foreground images, which only presented the treat object to be detected, whereas All the other contents in the baggage images constitute the background images, as the background dictionary was obtained from patches of them. The linear combination of these two directions was built for reconstructing the testing image. Usually, the testing image was assigned to the class with the minimal reconstruction error. However, this method could face such a problem in practical application. When a new type of baggage appeared, the performance of the algorithm will be significantly regarded. In order to overcome this limitation, we reconstructed the testing image only using the sparse representation by foreground dictionary. In addition, we used direction features instead of pixel features as the items of the foreground dictionary to provide multiple possibilities of the gradient values. The foreground images are consist of clean treat objects. We used the well-known methodology of sliding window to extract the pixel firstly. Each patch ZF with size W times W pixels of the foreground images is then converted into a direction feature YF. Considering the good performance of the self-descriptor, our proposed direction feature is based on similar properties that use relative strengths and orientation of gradient to reduce the factor of direction changes. We calculate the hair wavelength response in X and the Y direction on each patch. The dominant orientation is estimated by calculating the sum of all response within a sliding orientation window covering an angle of pi/4. Therefore, each patch is split up regularly into smaller 4x4 square subregions. For each subregion, we compute a few simple features at 5x5 regularly spaced sample points of size S times S. For reasons of simplicity, we call dx as the higher wavelength response in horizontal direction and dy the higher wavelength response in vertical direction. Horizontal and vertical here is defined in relation to the dominant orientation. Then the wavelength response dx and the dy are summed up over each subregion, and we obtain the sum of the absolute values of the responses. Absolute value of dx and absolute value of dy constant according to the sign of dx and dy respectively. Each subregion has an 8-dimensional feature vector, and the 16 subregions contain a 128-dimensional direction feature. After converting all the n patches into feature vectors, they all combine into a foreground dictionary D of size 128 times n metric elements. To deal with different contrast conditions, we take the columns of the foreground dictionary normalized to unit length. After the foreground direction was obtained, each patch of query images are needed to be reconstructed with the weighted sum of foreground dictionary, and each patch Z is slid over the query image in both horizontal and vertical directions. We first compute its direction feature Y, and then we calculate the sparse representation of Y using foreground dictionary D. In the sparse representation, X no more than T elements allowed it to be non-zero. The reconstruction arrow E is then defined as the distance of direction feature Y and its reconstructed direction feature Y'. If the arrow E of a patch Z is lower than the error threshold C, this patch can be classified as foreground, otherwise it will be classified as background. Our model will put all the patches which classified as foreground into a non-metric ZF, which has the same size of the query image. This candidate image ZF shows all the potential regions of the prohibited items direct detection. At last, we convert ZF into a binary image R and frame out the largest connected areas as the detection region. In our dataset, the images are separated to two classes, object and non-object. The number of object X-ray images of the training set are 200, and the number of object and non-object X-ray images of the set of validation and testing are 50 to 300 and 200 to 1,200 respectively. Therefore, the testing image have 5 types of baggage to compare the performance of different methods. These images come from the public GD X-ray dataset. Figure A gives the type of baggage which is used to build a background dictionary. We name it GD1. The other 4 types of baggage are also employed on our experiments, which are exhibited in Figure B. They are named as GD2 to GD5. In order to compare our method with MyRead's, we take a set of comparative experiments. For simplicity, the comparative methods are represented by the abbreviation. The method proposed by MyRead is named as FBWP, which means this method employs sparse representation of pixel features by foreground and background dictionaries. Our method named FWD, which means it uses sparse representation of direction features by foreground dictionary. Moreover, we use pixel features rather than direction features in our algorithm in order to show the contribution of the direction features and name it FWP. We employ F1 measure and accuracy as the evaluation protocol for the detection of guns in X-ray images. Table 1 describes the comparison of our method FWD and FBWP. When they tested on GD1, the performance of FBWP is better than our method. When they are tested on the other types of baggage, the performance of FBWP declines obviously. Compared with it, our method FWD obtains stable results. We also compared our method to FWP to illustrate the contribution of direction features used in our work. The experimental results are displayed in Table 2. From this table, we can see that the average performance of FWD is superior to that of FWP on the testing dataset. The experiment demonstrates that our approach is a robust method on different backgrounds to implement object detection. Future work, we will focus on solving the problem of scale invariance of 3 objects and employing our algorithm on a broader dataset. Thank you for listening. That's the end of my presentation.
Hi everyone. On behalf of the Aldo Moro University of Bari, I would like to welcome you here. My name is Vincenzo. I am a doctor and a researcher in computer science. Today, I would like to talk to you about the experimentation carried out and reported in the scientific paper called An Application and Integration of Machine Learning Approach on a Real IoT Agricultural Scenario, supervised by the authors reported in this slide. The aim of the experimentation is to make a forecast of solar radiation to encourage the use of IoT scenarios in the agricultural field. The solar index supports many critical decisions for campaigns, among which there is the desire to quantify the water needed for agricultural land. This value is used to calculate the reference evapotranspiration ATO throughout the Pinman mountain equation, a parameter that represents a water loss that is proportional to the actual evapotranspiration of the crop. The daily ATO calculation allows agronomists to meet the requirements of actively growing crops. This work is a part of an industrial research project called EcoLoop. The project focuses on the development of support systems to help various stakeholders in the reuse of refined wastewater in agriculture. As can be seen from the architecture, the project is very large. The red circle denotes the location of our work of forecast solar radiation, both in situations where the data is missing and to meet real problems related to agriculture. To overcome this problem, the project idea is to build an easy-to-use system embedded in a modern IoT agricultural scenario to predict solar radiation, to better plan water stress and supply of agricultural land. The implementation of the project considered a multi-layer perceptron MLP as a basic classifier. MLP is a feed-forward neural network in which the connection between the nodes do not form a loop. Any continuous function that maps input value to an output range can be closely approximated by an MLP with a single hidden layer. The forecasting system is integrated considering 3 different time forecast horizons, which will be better explained later. The dataset was acquired by the industrial partner of the project and contains data for a period of time between 1 July 2017 and 2 January 2018. The database concerns the daily average value. For experimentation, it was divided into 75% for training, 25% for test. The variables considered are shown in these slides. Each feature was recorded by weather station specifically installed on the respective Apulian agricultural land. Finally, a preprocessing phase was carried out on the data with the aim of cleaning. In this work, the solar index prediction was performed considering various combinations of input variables. The first combination considered past solar radiation value used to make predictions of future solar radiation values. The second combination considers previous value, maximum temperature and the daily sunshine hour for the forecast of solar radiation. Finally, the future solar index value for the third combination are predicted using the maximum daily temperature, daily sunshine hour, and humidity. As mentioned earlier, 3 different time horizons were considered for forecasting purposes due to different periods of water supply and water needs of the plants: 1 day, 3 days, and 1 week. This slide shows the project pipeline summarized in 3 main steps. First, the MLP was trained with daily data in order to obtain predictions with previous horizons. 2. For each day X of the training interval, the network was powered by the data mentioned above. 3. Finally, give the relative actual values of a specific day, the network is able to provide the forecast of the expected average solar radiation within 1, 3, or 7 days. Training has been performed considering 10 epochs and the squared losses cost function. The following table presents the details. For example, number of epochs, number of hidden layers, numbers of neurons, activation function, batch size, cost function, optimizer. 2 common metrics have been considered: the root mean square error and the mean absolute percentage error. RMSE measures difference between two time series as the predicted value by one of the models and the observed one t times. MAPE measures the accuracy percentage between the value and its forecast. Now, let's move on the result part, which finalized what we have said so far. The RMSA MAPE and time value will then be illustrated with respect to the three configurations illustrated above. The illustrative tables will be three, as there are 3 time horizons: 1 day, 3 day, and 1 week. Now, let's look at the results of 1-day horizon forecasting. The first column represents the 3 feature combinations. The things that stand out are the results of the first configuration, which are clearly better than those of the other 2 configurations. It can be seen that the RMSA MAPE and time are smaller than the other 3 configurations. The same thing can be seen with a 3 days forecast of solar radiation. Even if the time forecast widens, we notice that the first configuration always remains the best. On the other hand, observing a 1-week time forecast of solar radiation, we can see that the values are even thinner than the previous observation, asserting the same value of RMSA MAPE and time equal to configuration 2. This makes us understand that we could also use the max temperature and the sun hours features to predict solar radiation. This last concept is confirmed by the following graph, which confirms the similarity of the 2 distributions of the data. In conclusion, to summarize, the experimentation showed that the use of the standard predictors achieves the best results for each time horizon in terms of RMSA. But in addition, it was discovered from the data that it is possible to predict solar radiation even if its values are not available, using the data obtained with the cheaper sensors, for example, temperature and/or humidity. Thank you for your attention.
Okay, thank you very much. So we'll go to our next session. In session F, medical imaging
everyone.
and applications. So our first presenter is Zhenyue Zhu. She'll present a novel ECG signal classification algorithm based on common and specific components separation. Okay, please begin.
Okay, hi everyone. Now I'm going to start my presentation. My presentation will cover the following aspects: introduction and classification model and numerical experiments. Electrocardiography is a recording of the electrical activity of the heart. Many algorithms like SVM and N has been proposed to classify ECG signals. In this paper, we propose a novel ECG classification model based on separation of the common and specific components.
Better speak louder.
The idea is...
Speak louder.
Okay, louder. Is it okay? Hi. The real-world signals consist of different basic components and various combinations of which give rise to different classes. Any class of signals may have some common components as well as its own specific components. So our goal is to design a classification model based on the specific components. The notations are as follows. V is the column vector and span M is the column space of a matrix M. Projection Vj is the projection of a vector V onto span A. To build a classification model is essentially to design a classifier chi mapping from signal space to a label set. In addition, we also define a feature map phi which maps a signal to a lower dimensional feature vector to capture the characteristics of the signal. So we aim to define a feature map phi based on the specific components, and thus the classifier can be determined by phi. At first, we consider the simple case of a binary classification. Suppose we are given samples from two classes, P samples for class 1 and Q samples for class 2. The corresponding sample matrices are S1 and S2. We assume that there are three sets of vectors F, G, and H such that each sample Si in class 1 is a linear combination of F, J, and Gk, and each Si in class 2 is a linear combination of Fj and Hl. We rewrite them in the matrix form, which is equation 1, where A, B, C, D are the coefficient matrices. We call Fj the common components of the two classes, Gk and Hl the specific components of class 1 and class 2 respectively. We classify the signals based on Gk and Hl. We notice that the choice of F, G, and H is not unique, so we must put some restrictions on them to determine a unique solution. From equation 1, we have span S1 or 2 is the subset of span F plus span G or H. To reduce redundancy, it's natural to require that the equality holds and all the basis vectors are linear independent. So under the requirements, it's easy to see that span F is an intersection of span S1 and span S2. So if we are given the sample matrices S1 and 2, we can calculate span F by equation 4, and F can be any basis of span F. It follows from 3 and 4 that span G and span H are the quotient spaces of span Si by span F respectively. Formula 5 means that we can split the space into a direct sum as equation 6. See figure 1 for an illustration. As a corollary of equation 6, any sample Si in the two classes can be uniquely decomposed as the projections of Si onto span F, span G, and span H. Keep the specific part for classification. Let tilde Si be the projection of S onto span GH. Then calculate the angles between tilde Si and the two subspaces. We then get the two angles alpha and beta measuring the closeness of tilde Si to the two subspaces respectively. Based on the two angles, we can define a simple feature map phi S and a binary classifier chi, which equals 1 if cosine alpha is no less than cosine beta and equals 2 otherwise. Since the assumption we made on FGH are quite idealistic, and the calculation of span F as the intersection of the two subspaces might become unstable due to noise in the signals. The basic model should be improved to be more robust and stable. We relax the assumptions and suppose there are two sets of basis vectors F1 and F2 such that equation 10 holds, where F1 and F2 are required to be close to each other. The problem is to find Fi in span Si such that they are close to each other. Adopt the correlation coefficient rho Fg to measure the closeness of two vectors. According to classical results in canonical correlation analysis, there exist vectors U and V satisfying the following iteration process. In each epoch, UK and VK are the most correlated vectors in the orthogonal complementary subspaces of UK and VK respectively. The process will end at round R, where R is the minimum of rank Si. This can be realized by the MATLAB built-in function Canon core. We notice that row UK VK is descending over K, and so we can set a threshold row 0 and determine an index K0 such that row UK0 VK0 is the smallest one that's no less than row 0, and then we select the first K0 vectors of the two sets to determine the matrices F1 and F2, and span G, span H are the corresponding quotient spaces. Since row 0 determines the ratio of the number of common components to the specific components, we usually set it to be 0.5. And finally, the feature map can be similarly defined as in the basic model. Table 1 shows the pseudocode. In the training phase, we take S1 and S2 and the correlation threshold row 0 as input, and use the MATLAB function to calculate row K, UK, and VK. Then determine the K0 and the matrices U and V. Finally, output G and H, which are going to be used in the testing phase. For now, we have constructed the binary classification model. As for the multi-class classification model, we use a voting strategy. And we have done some experiments. Our dataset is from MITBIH arrhythmia database. Each sample is a heartbeat, and all the heartbeats can be classified into 5 types as V, F, Q, and M. Before classification, there is a pre-processing phase, including 4 steps. First, extract each single bit from the ECG signal recording number 119 according to the annotation file. Second, normalize the length of each bit to 400 by linear warping transformation. Third, shift the maximum of each bit to the center of the time interval. Finally, subtract the mean of each bit so that they are 0 mean. Fig 4 shows some examples of the 5 types that has been pre-processed. To perform a binary classification, we set V type be the positive class and non-V type be the negative class. Then randomly select 100 bits from each class for training and 300 for testing. The CCA procedure will produce 100 pairs of correlated vectors. Fig 5a plots the correlation coefficients, row UK, VK decreasing from 1 to 0 as K grows, and the 5b plots the first 5 pairs of correlated vectors we have calculated. Figure 6 plots the distribution of the future point phi Si for different choices of row 0. We can see that when row 0 is small, the feature points are spread. The feature points have a large spread and locate far away from the separating line. And when row 0 is large, the feature points are more concentrated and locate more much nearer to the line. We also perform binary classification on different recordings with results as in table 3. On average, the accuracy is 94.1, the sensitivity is 95.7%, and the specificity is 92%. 0.5%. And table 5 is the confusion matrix of multi-class classification experiment. We can see that type Q is the most recognized type with 91.7 correctly recognized, and type S is the most difficult to be recognized with only 48.5 correctly classified. We also compare the proposed method with other works showing roughly the same level of performance. Since our model has a much simpler architecture and no specific techniques are used in the preprocessing stage, it is rather promising. In conclusion, our method is easily implemented and has a good mathematical foundation, and the design of classifier is totally data-driven with no prior knowledge of data or complicated feature engineering. However, we have to point out there are some limitations, like the feature vector of two angles, alpha and beta, might be too simple to achieve a high performance, and the assumption of linear independence between the components of ECG signals might be too strict a condition. And finally, it remains a problem that how the choice of the threshold of 0 affects the outcome of classification. My presentation is over. Thank you everyone.
Thank you very much. So the next paper is a novel deep learning approach for liver MRI classification and HCC detection. And Messaoudi Rim will be presenting. Go ahead.
Hello everyone. Today I'm going to present our paper entitled A Novel Deep Learning Approach for Liver MRI Classification and HCC Detection. My talk is divided into 5 parts. Firstly, I will introduce our work and explain our motivation. Later, I will present some related works. After that, I will explain our deep learning approach. In the next part, I will present some results and the validation step. After that, I will end the paper and give our future work. Let's start by the context of our work. So in our work interested in liver cancer, especially the hepatocellular carcinoma, it's the most common type of liver cancer in adults and develops in liver with cirrhosis. Diagnosis of this cancer is realized through different modalities such as MRI, CT scans, and ultrasound. In our case, the interest is on medical imaging, especially the dynamic contrast enhanced magnetic resonance imaging. It consists on the intravenous injection of contrast agents, while images are acquired with high temporal resolution to capture some image sequences. So HCC detection is a very challenging task, especially from dynamic contrast enhanced MRI. Also, during our study in the literature classification, we didn't find several methods that use CNA to classify liver images, especially for HCC lesions. Also, we found that few works use deep learning to detect HCC from different DC MRI imaging. So how can we ameliorate HCC detection? The objective of our work is proposing a novel deep learning approach based on the CNN architecture that allows HCC detection and localization in DCE MRI images. The goal also is to increase the size of the F1 measures compared to our previous work while trying to keep an interesting accuracy rate. You found in the slide our previous work. The first work is based on the SVM method or the supervector machine method, and the second is based on the unit method. Let's move now to see some related works in this context. So this table mentions some related works. the first work proposed an automatic CNN with multi-magnification input images by using the CNN technique. The second work proposed a method that classifies common hepatic lesions by the use of multiphasing MRI. The applied technique here is the deep learning system and also the CNN architecture. The third work is a recent work of our team. It integrated deep learning into MRI image and proposed a framework for HCC detection by the use of UNet technique. The fourth work is also a work of our team. It proposed a parallel framework for HCC detection from dynamic contrast enhanced MRI sequences and by the use of the super vector machine classification. The last work presented also an approach that generates synthetic medical by the use of generated adversarial networks. If we discussed this related work, we found that all the previous cited works have really revealed the importance of applying classification methods to classify medical images and data. But the problem that they do not deeply use the CNN to classify liver MRI, especially for the case of HCC tumors, also to reach high measures of accuracy. We move now to show the proposed the approach. This slide mentions the proposed approach. It's based on 5 different phases. The first is the phase of pre-processing and the preparation of the fragments. After that, the training step in order to form the CNN model. After that, you have the prediction phase, and after that, we test the predicted model. After that, it's a validation step. Each one of these phases will be explained in the next slides. For the proposed approach, for the pre-processing step especially, during the MRI process, the radiologist or the doctor takes 3 different MRI images for each patient, depending on the time after the contrast injection. This will take into account the evolution of information in these 3 different images sequences, as mentioned in figure 1. Here we found 3 different phases. In our work, we will use the second and the third phases because the first phases do not really offer a lot of information about the patient state. After the preparation of these images, we found that each image will be divided into fragments in order to form the deep learning database. We move now to see our model. It consists of a consecutive of convolution blocks dedicated to extract and identify image features. As we mentioned here, these images are interconnected with a fully connected block that classifies fragments. For the prediction step, each fragment of the preprocessing step will be called with a number. The value 0 will be attributed to a normal fragment, and the value 1 will be attributed to a cancerous fragment, as we mentioned this figure. We move now to see the results and validation of our work. This slide presents our deep learning database description. It's composed of a set of fragments, totally around 47,000, divided into training data and testing data. For the training data, we have employed around 18,000 cancerous fragments, and for the normal fragments, we have used around 29,000 fragments. After the training of our model, we find, and after the execution of the model, we found that the accuracy rate reached 97% of accuracy, and the loss rate was 0.03. To test our model, we have taken enough patients of the dataset in order to predict the existence of HCC tumors using the proposed model shown in the recent slides. This table mentions the evolution concerns the phase 2. Based on the obtained results, the model is able to predict the medical status of the liver. For phase 2 results were around 18% for the sensitivity, 71% for the accuracy, 92% for the specificity, and 74% for the F1 measures. For the phase 3 evolution, we found that the sensitivity rate was around 81%. For the accuracy, it was around 68%. For the specificity, it was 90%. And for the F1 level, it was 73%. Regarding our previous studies mentioned in the related works, we found that F1 score level had been increased and reached respectively 74% and 73% for phase 3 and phase 3, considering the model proposed by Fabrizio. It's the unit method. It has been increased also from 66% in the second model, which uses the SAM architecture. Also, based on this result, we found that sensitivity rate has been increased in phase 3 from 76% to 81%, and sensitivity rates have been increased respectively from 87% and 82% to 92% and 19% in our case. To conclude, we presented this work deploying the approach to the MRI classification and HCC detection by the use of the CNN architecture. As future work, we aim on ameliorating the performance of our algorithm by including other semantic techniques in order to detect, to enlarge the detection process. Already we have submitted this work in the International Journal of the Pattern Recognition and Artificial Intelligence, and we did not yet receive the remarks of the reviewers. Thank you for your attention.
Thank you very much for your presentation.
Welcome everybody, and I'm Vincent and I'm going to present the sit-to-stand test for neurodegenerative disease video classification. This is made also by Professor Donato Impedovo and Professor Giuseppe Pirro. So we are from University of Bari, Aldo Moro, and that's it. So the proposed system. The idea is to, starting from video recordings of patients and control subjects, which are performing a 5-time sit-to-stand test, the design system is capable of extracting relevant patterns for discerning patients with dementia from healthy subjects with an accuracy of 80.8%. So why neurodegenerative disease? Because those are diseases that are incurable at the moment, and are also a set of pathologies that are affecting the central nervous system, which are characterized by a chronic process of cell death of neurons. And among the most common, we have the Alzheimer, the Parkinson, the Huntington, chorea, the amyotrophic lateral sclerosis, and various kinds of dementias. For this experiment, we used the 5-time sit-to-stand test, which is a very challenging test from a computer vision perspective, and it consists in 2 phases: the sit-to-stand transfer phase, which is where the patient stands up to reach the standing position, and is also called the stand-up phase, and the stand-to-sit transfer phase, where the patient, after reaching the standing position, resides. This is also called the sit-down phase. The application is the following. The system uses simple video cameras, 2D RGB camera, to extract information of interest. Therefore, the system can be easily integrated into daily activity, daily life, without excessive effort, because even when patients don't have to wear anything. That's it. The data set is small, and it's composed by only 10 people, 7 patients with dementia in various stages, and 3 subjects of the normative sample. We didn't add more control subject because the control subject age was balanced. So there we have people in their 70s, 80s, and we have the normative sample with same age. That's important. And also another thing is that the exercise was taken by using 3 cameras placed at different angles, right, left, and center, and the video was stabilized at 20 frame per second. This is the classification pipeline. The aim of this project is to binary discern people with dementia from people without. So the pipeline is the following. We have the video is split in frame, and for each frame the pose is estimated, and for doing so the user is asked to select the body of the patient to analyze, and then the barycenter is kept into consideration, and all the joints coordinates which are closer to the body center are analyzed. Then we extract the coordinates of key point, remove extreme values, filter the values with the Kalman filter, perform the phase segmentation, feature extraction, oversampling to balance the dataset, feature selection, and classification at the end. So for the video preprocessing, as I said, we use the OpenPose library that extracts the coordinates of the joints from each frame, as you can see from the pictures on the right. And the preprocessing is the following, because OpenPose can get bad results sometime when some joints are not visible. Those are replaced by zeros, and thus we have gaps. We fill the gaps with linear interpolation, and the Kalman filter is used for smoothing out the coordinates of of each joint. The segmentation is kept into consideration the angle between the hip, shoulders, and knees, and these are used for understanding when the patient reached the standing position or it's is sitting. For the feature extraction, we used the features in table 1, as you can see on the left, and those features provides every feature provides time series. So we synthesize the time series with the statistics in table 2, like mean, median, standard deviation, 1 and 99 percentile. For the classification, we used several kinds of classifier, SVM, random forest, AdaBoost, and so on. But the best accuracy was reached with the feed-forward neural network with 858 neurons in the first hidden layer and 572 in the second hidden layer with ReLU activation function and Adam as solver, which achieved the 0.808 accuracy. And we used also the extra tree classifier as feature selection technique. It's important to say that for this classification, this interpatient separation scheme was used, where the feature extracted from some patients are used for training, and feature extracted from other patients or other people, different from the people used for training, are used for testing. So it's different from the idea of doing the 70-30 separation, like 70% of the entire dataset used for training and 30 used for testing. This is much more robust. Okay, this is the ranking of top 20 features selected. As it's possible to note, the 55% of top 20 meaningful features are synthesized from the neck movement, followed by head, left hip, and right hip. Therefore, differently from the global medical assumption, which is measuring legs, muscles, and shoulder muscles activities, the neck and hip are the clearest winner when it comes up to sit-to-stand classification with computer vision and image processing technique. Thank you for watching.
Hello, ladies and gentlemen. Today we would like to share about clinical decision support systems for predicting patients liable to acquire acute myocardial infarctions. And we are from Central Taiwan University of Science and Technology in Taiwan. This slide shows the authors of this work and our pictures. This study aims to develop a CDSS for precisely predicting patients who are liable to acquire AMI based on the data retrieved from the NHIRD of Taiwanese. NHIRD is the abbreviation of National Health Insurance Research Database. We considered the main risk factors and the comorbidities of AMI reported in literature, and the key factors suggested in our previous studies, because living habits, physiological signals, and the family histories of patients are not available in the NHIRD. They were not considered in the current study. Table 1 lists the ICD-9 codes of 12 comorbidities included for analysis and to be considered for denying the CDSS models. In addition to presence of these 12 comorbidities, patients' ages when individual comorbidities were diagnosed, as well as follow-up durations and annual physician visits of the comorbidities were also considered, accounting to a total of 50 features to be included for CDSS deny. IGS algorithm was adopted for the CDSS deny in this study. IGS is the abbreviation of Integrated Genetic Algorithm and the Support Vector Machine. In IGS algorithm, GA is used for setting the optimal SVM parameters and the significant features for constructing the SVM models. The chromosome pattern and the software flowchart of IGS algorithm are illustrated in Figure 1. In this study, 2 independent training and test ITT experiments were performed to verify the prediction performance of denied CDSS. During the training phase, 10-fold cross validation and 3 objective functions were used to train and validate the CDSS. Instead of accuracy, as indicated in equations 1, 2, 3, combination of accuracy, sensitivity, and specificity, area under the ROC curve, AUC, as well as G-means, respectively, were used for obtaining the model with best prediction performance. Data of 6,087 AMI patients and 6,087 non-AMI patients, each includes 50 features, were acquired for denying the predictive models. The comorbidities and other comorbidity-related features selected for denying CDSS models based on 3 different objective functions, OB1, OB2, and OB3, are also shown in Table 2, columns 5 to 7. Notably, although age was exactly matched and have no difference between AMI and the non-AMI groups, it was selected and adopted as an important factor for denying the CDSS models based on all 3 objective functions. As shown in this slide and the following 3 slides, although the future combinations are different among three models. Presence of comorbidities and the comorbidity-related features were mostly selected. This slide shows 12 comorbidities between non-AMI and AMI groups, and the comorbidities selected by three objective functions, respectively. This slide shows the difference of mean age when each comorbidity was diagnosed between non-AMI and AMI groups, and these features selected by three objective functions, respectively. Follow-up durations of the comorbidity of non-AMI and AMI groups are presented in this page. Outpatient and inpatient visits per year for the comorbidity of these two groups are shown in this page. The predictive performances of CTSS models denied using the IGS method with floating threshold method are shown in Table 3. As indicated in the table, the obtained accuracy, sensitivity, specificity, and AUC were all good. There are 39, 23, and 33 features selected for constructing OB1, OB2, and OB3 models, respectively, although OB2 model adopted the fewest features for model construction. Its predictive performance was similar to both OB1 and OB3 models. Furthermore, it can be observed that, except follow-up duration of hyperlipidemia, 22 features of the 23 features selected by using OB2 were also selected by OB1 or OB3. Similar phenomenon can also be observed in our previous study. Our experiments results show that using the IGS algorithm with presence of comorbidities and other comorbidities-related features are able to deny strong CTSS models AUCs greater than 0.8 in predicting patients who are liable to acquire AMI in the near future. However, further improvement in the predicted performance still needs to be conducted. Future studies will focus on aggressively screening patients who are liable to acquire AMI and administrate effective M-health interventions for promoting health education and monitoring acquired comorbidities to prevent occurrence or recurrence of AMI. Thank you very much for your attention. Have a nice day. Goodbye.
Keynote speaker, Professor Farida Shariat, will have a 10 minutes break, and we will resume at 10:35. So right now I will share the screen and have the talk shown on my screen. Can you see my screen?
Yes.
Yeah, so Professor Farida Shariat will be presenting the keynote in about 8 minutes. It's related to pattern recognition and AI in multimodal medical image analysis. applications and challenges. And Professor Chariot is a professor of computer and software engineering and director of the LEAF 4D Laboratory of Polytechnique Montreal. She is a member of the Biomedical Engineering Institute and the Research Center of Saint Justine. Saint Justine is a hospital for children in Montreal. And so we look forward to her presentations in a few minutes. In the meantime, relax. Coffee break or tea break. We'll see you again. Stay tuned.
The next keynote speaker is Professor Farida Chariot. He is professor at the Polytechnique of Montreal in Canada. Professor Chariot is the head of level of image processing, specialist in medical imaging. Welcome, Professor Farida Chariot, to give keynote speech.
Hello, everyone. First of all, I would like to thank Professor Suen to giving me this opportunity to share with you the work that I have been doing with my team during the last decade. And I thank also Dr. Tang for the introduction. So I will show you some applications in medical field where pattern recognition and artificial intelligence had really an impact. In the same time, I will also show some challenges that we are facing until now and should be handled in the future also. So I will start with one application, which is the diagnosis of ocular diseases, where pattern recognition and artificial intelligence did really a lot. You can see here, can you see my mouse? Yeah?
Yes.
So I'm showing here a fundus image where you can see that we can get the surface of the retina with many anatomical structures like the disc, the optic disc here, the vessels, and also the macula. And the doctors, from getting this image, they can look for some indicators which will show some problems of some specific pathologies like diabetic retinopathy, age-related macular degeneration, or glaucoma. And it is really very interesting because this kind of images are acquired by non-invasive cameras, and they are not very expensive, so it is really a good way to screen in time all these kind of pathologies. I will start with diabetic retinopathy. So as you can see, we have many indicators, starting with microaneurysm that we can see here. They are very small. Then they can progress to hemorrhage. You see here some hemorrhage on these images. And when we can have also some bright lesions like here called exudate. And when it is really severe, you can have even neovessels that will appear here. And when you have only one lesion like this, the doctor can say that there is diabetic retinopathy. And until recently, most people were working on segmentation and are trying to segment the microaneurysm to see if the patient is healthy or not. So the question is it possible to use artificial intelligence to help doctors? The reason is that you have, if I just talk about the Canadians, we have 40% of Canadians that with diabetes that are not screened for that. And we know that all patients with diabetes can have in their life maybe 10 years after or 20 years after a diabetic retinopathy. So it is very important to diagnose this pathology, because if it is diagnosed early, then we can do more than if it is really already severe. So it is important to do that. And we see that also we have the telemedicine network that are emerging. So even if some people don't have access to the doctor, mainly because they are living very far from the cities, we have the opportunity to get their images using these simple cameras and with the telemedicine network. But still, the readers are really limited, so we don't have enough number of readers to take in charge all these patients. This is why the artificial intelligence can really facilitate the early screening of this kind of pathology, and also limit the patients who will see the specialist, because until now we have really the ratio between the specialist and the number of patients is really very low. So we would like to send to the specialist only those who really need them, and try to do some triage for the patients that don't need to go right now to the specialist. So we started with classical techniques like extracting features from this kind of images. And in this work, we tried also to get not only the microaneurysm, but the hemorrhage also. And the steps are classical, so you need to do some pre-processing of this kind of images, and also extract features, classify the different candidates, and give a probability map. What we did new here is that we are looking for dynamic features, like we named them here, because we are here we have the watershed method, so we are doing morphologic flooding of the retinal image, and we are looking for some characteristic like solidity, elongation, etc. at different levels of flooding. So we are not looking only the last result, but we are looking during the flooding levels how these characteristics are evolving. And you can see here that we can see that the difference between the red lesions and the non-lesions. So even if you have many candidates, when you are extracting in the beginning the candidates, you can eliminate those who are not lesions and keep only the lesions. We had to evaluate the algorithm on public data set to be sure that we can compare with the others. So we have here the Messidor data set with 1,200 images, and you see the classification which is done here. Indeed, when you want to screen, you want just to see if the patient is healthy, which is R0, or non-healthy. So for sure, the best thing to do is to do the grading after, but it is at least necessary to screen to be sure that the patient don't have to go to see the specialist. So you see here the accuracy obtained by the algorithm with respect to the accuracy obtained by the human expert. And usually we have also this problem of variability between experts. So if you have an automatic way, then you can eliminate this variability when it is reliable indeed. We can compare also the results with other people, and we can see that this method did something interesting, and maybe because when you see also how it compares here on our private database to the expert, you can see that at least you have a reduction of 60% of the clinical burden on the ophthalmologist, and this is what we want to do in this case. So we don't want to have a lot false positives because we don't have enough specialists for that. Now, because deep learning is really interesting and did many interesting success also in different applications, so we also did this investigation and see if it is possible to use deep learning to facilitate the screening of the DR. Because you can, maybe you saw many algorithms that are published and many work, but unfortunately when you try to validate these models on your own data set, the success is really limited. So we are doing work to see how we can overcome this kind of challenge. This is why we decided to have work on the building a Canadian data set, because as I said, when you are using other algorithms that are already published, they don't perform exactly how they do on their data sets. So we started with an annotation platform. And what is interesting is that we are not working with technicians or readers, but we are working with retinal specialists who can really help in the annotation. For sure, you cannot ask a specialist to annotate from scratch. So what we are doing here is to pre-annotate with our previous algorithm and then just ask the clinician to correct, or so the burden is really limited. And we are here also interested to annotate biomarkers. So we are not just annotating at the image level and give the diagnosis, but we want to also explain at the end the decision, because if you are just doing an image level annotation, if your system said that there is nothing there, there is no diabetic retinopathy, maybe there is another disease that you are missing. So this is why by doing the annotation of biomarkers, we want to extend our model to different kind of ocular diseases and not limited to DR. So we discovered many things by working with these clinicians. We can have many disagreements during the annotation. Sometimes it is due to the artifacts that you can hear. So I can have just something that is similar to the microaneurysm, but it is not, because it is a problem of the lens. So they can be really misclassified as microaneurysm. You can see also here the inter-annotator agreement on the table. So you see that I have here 3 graders, and they can disagree, unfortunately. And this is why I said if we have something that is reliable after the consensus and also the majority vote, we will build a data set that can be more reliable than the public data sets that we had now. The other point is the quality assessment for this kind of images. In real medical situation, we have many poor quality images, and we have to work with that. So when you give a decision, you have to be sure that your image was really exploitable, and it has a good quality. And what is specific for these images is that you cannot define the quality like in the computer vision community, because the image is the good quality if the doctor is able to give a diagnosis. So you have to follow this kind of standards like the Scottish Diabetic Retinopathy Grading System to be sure that you are considering really the good definition for the quality. So this is why we worked with the clinician to define a score based on their definition of the quality on this kind of images, and it has to be integrated in our system to be sure that the decision is reliable or not based on this score. Another thing that people are not doing is that the doctors in general acquire many images for each eye, so they will not take their decision on one image only. So usually they have some images centered on the optic disc, others centered on the macula, but they are looking to all these images before giving the diagnosis. So it is not fair to build a model that is looking only for one image, so we have to integrate that. And the challenge of how to combine them is still an open problem, and we are doing research by testing many techniques by combining these different images. Also, as I said, we are interested to annotate biomarkers, so at the pixel level, but you can say that it is really time consuming, so we cannot have millions of the annotated data if we go only with that. So we proposed a way to combine the image level with the pixel level. So this is what we are calling an architecture which is weakly supervised, because you will have some annotated pixel level images like the biomarkers, the lesions, and you will have another kind of set of images that are annotated only at the image level, which is more easy to do. So we have three branches. So you have the branch for the generalization block, which is the image level diagnosis. You have also the red lesions to detect and the bright lesions, because I need both to be sure that I will give the right grade for this pathology. So then this is why we are calling it a multitasking, because you have to train your model to learn these three things. As I said, we are working on with the clinicians to annotate the images with all these biomarkers, and we have already, from the Mesidol dataset, 200 images that are annotated by the clinicians, which is really something interesting even for the research community, because until now we had very, very few images annotated for the vessels, because as you can see, it is time consuming to do this for the vessels for sure. But we are doing this, and what is important also is to follow the guidelines from the Canadian Retina Research Network, because it can be different from the others. And if we want the model to work in our data set, then it is important to take into account this kind of standards. An ongoing research also is looking to an approach based on graphs, where we will have a representation of these images based on the biomarkers using graphs, and do the classification of the graphs for the diagnosis. And what is also interesting is that we are targeting to integrate OCT, which is optical coherence tomography, B-scans, also in addition to the fundus image, because usually for the macular edema, which is usually a problem in the macula, and it is really very severe, and the patient has to be referred to the clinician as soon as we can detect something like this. But to be sure, we have usually also to acquire an OCT image to confirm the problem. So this is why we would like to integrate this kind of exams also, because as I said, if the doctor is using many exams to classify pathology, then we should consider that also in the model. We worked also on the detection of the vessels, because in general, in the CAD systems in this pathology, all the missed vessels will be considered as lesions, because I showed you before the lesions could be hemorrhage, but if you just miss the detection of the vessels, then all the rest will be considered as lesions. So it was necessary to improve the algorithm to detect the small vessels, and this is why we use this multi-scale perceptual method. And we saw that the improvement was there. And as I said, also it helps to pre-annotate our vessels when we decided to annotate the vessels on the images. We have also some work on using deep learning to detect and also to classify, because when you are using some standard UNet segmentation, you will have a good segmentation of the vessels, but the classification between vein and arteries is very hard. And this is very useful when you are looking for some also cardiovascular problems from the retina. There are many work who are interested to that, because we know that our vascular system is the same in our body. So if you start to have some microvascular problems in the retina, it can be related also with some problems in the heart. And unfortunately, the small vessels of the heart are really difficult to acquire until now. So this is why if you can detect this from the eye, then it will be very interesting. And this is something that we are interested to do. As I said, for the classification, it is very hard for the unit because the receptive field is relatively small, so you need to have a larger receptive field to do the classification. And this is where we proposed something like this, like adding a low resolution branch to add this information and to allow a better classification of the vessels, and the accuracy improved by doing this. We worked also on the glaucoma, which is the other kind of problems that we can have. And usually the doctor is measuring this index, which is cup to disc ratio. We can see here the disc. So they are measuring this relative ratio between the disc and the cup. Because in the glaucoma, we can have the degeneration of this optic nerve, and we can see it by measuring this, but it is not enough to detect really the glaucoma. They are taking OCT images also to confirm that. So we said maybe they are not exploiting very well all the information that we have on the fundus image, and this is why we started to do something to understand what is a normal disc. So in the normal population, we build an atlas to see what is a normal disc and what is the variability inside the population, because we are all different. So each subject is different from the other. So how we can say that one is normal or not. So this is why we try to analyze better this kind of images and see how we can build this atlas and see if it is possible then to characterize patients with glaucoma, because they will not be in the normal population. We have many steps to do that. So the first step is to segment these images, find a representation that will be relevant to highlight the abnormalities of the disc, and do some registration to construct our atlas and our average model, and see how do the statistical analysis to distinguish between a normal and a normal subject and a patient with some disc abnormalities. We decided to consider only these 4 regions. So you see we are keeping, instead of keeping only the cup and the disc, we are keeping also the vessels, because our hypothesis is that the configuration of the vessels will be different depending if the patient is normal or not. And with that, for the registration, we are using log demo to evaluate the difference between one subject to the other. You can see here how the configuration of the vessels are changing. Here's the source to the target. Now we need to register to construct our atlas. So the way we are doing this is that from the images, we consider only the regions that I showed you, so this kind of representation. And then this is the set of my healthy population for now, because we are talking about atlases. And after that, I will take one of them as a reference, and I compute the displacement field from each one to the reference. By doing this, by using log demo registration, and then I construct iteratively my reference by computing using this equation. At the end, you will converge to the average model. So this is how we do it. And after that, I need to analyze also all this displacement to see if there are some components that will show me something interesting. And this is how we found that indeed there are many components that will explain the variability modes on the healthy population, as you can see. And from that, I can see the variability that is acceptable in a normal population. So if I'm outside of this variability, then I can consider that I have maybe an abnormality of the disc. And this is how we decided to analyze some of these components and see if there is a difference between the atlas, the healthy subjects, and the diagnosis glaucoma. So we had some subjects with glaucoma, and we saw that there is really a difference between the two other sets. And it was encouraging to say, maybe we have to continue and see if there is a way to find a score for the stratification of the glaucoma. And this is what we did, and we found that indeed when you are using the atlas, you can get a better area under the curve. You have with respect to the CDR, which is the index that is used by the doctor. So it was interesting to see that. And yeah, so when you are combining different components, you can find that it is it detects early signs of the glaucoma, and this is not only by using the capture disc, but we see also the displacement of the vessels that have also impact on that. My second application is about cardiovascular image analysis. So in this case also we did many classical techniques of pattern recognition and artificial intelligence for the 3D reconstruction of the coronary arteries. Indeed, the old system was to send a contrast agent in the vessels. This is why we are acquiring angiographic images, and to see how the narrowing of the vessel is, because when you have a stenosis, you have this narrowing of the vessels, and you can even have some problems for some blockage. So it is very important to see that, because if it is severe, then it can lead to infarct. But when you are taking this kind of images, the doctor has to decide which incidence angle to consider. Since it is not symmetric, they can miss totally the problem. So this is why the 3D reconstruction will show you exactly the structure and see if there is a problem or not. So it was something that was really important to do, especially because we have many images taken at different angles. So it is important using stereo vision approaches to do that. So our first work was done with classical methods, but in this kind of techniques you have also the problem of motion. So the patient is fortunately breathing, so you need to compensate for this problem of motion. So you had to, in addition to the pre-processing, standard pre-processing like filtering and something like this, it is necessary to correct for the motion of the breathing. Now, to detect the vessels also for the segmentation, you need to see exactly to isolate the region which is really moving, because the heart is also moving. So we had some work to do to find exactly the binary mass to be sure that I am taking only the coronaries and not the other structures that can move also. So by doing this, you will be able to do a segmentation of the coronary arteries, which is the prerequisite for the reconstruction, as we can see here. But indeed, as I said, with these classical methods, we were able also to annotate some images and do some deep learning technique to segment the vessels. So it can be interesting to do that, because for sure, sometimes the classical techniques will fail to find the small structures, and we are working now with deep learning techniques to enhance this kind of segmentation. The other thing is that when you are doing reconstruction, you need to synchronize your sequences, because we acquire a sequence of images and they are not acquired simultaneously. at different angles. So you need to find the corresponding frame to the other frame to have the possibility to apply the stereo vision approach and reconstruct in 3D from a pair of view. So it was important to synchronize the two sequences, and it was also done by deep learning. So it was possible to do this synchronization using this method. You can see here a deep CNN that was pre-trained, because it is really difficult to get a lot of annotated images. So this is why we are doing transfer learning to fine-tune the model at the end to be sure that I will have the synchronized frame. So we compute the similarity matrix based on the features extracted from this model, and then from that, with pathfinding, you can find exactly the frame corresponding to each one on the other sequence. So we can see here some examples of the results where the sequences are more synchronized. And from that, you can go further. This is an ongoing work with to do the spatial matching, because to reconstruct in 3D, you need to match some primitives on the pair of views. So we can, for example, here reconstruct the bifurcation points, and this is why we are doing something based on graphs. And it is also based on convolution neural networks on graphs to do this corresponding between two synchronized frames to get the 3D reconstruction, because we have in the DICOM system many parameters of the acquisition system. Based on the matching, you can get the 3D reconstruction, as I showed before. I don't know if I have still time to go with other application. Is it okay? Nicola?
For me, it's okay.
Okay.
Yeah, go ahead.
Okay, so the other application here is about the classification of fluorescence microscopy images. So as you can see here, a cell is partitioned in many organelles, and in each organelle we have proteins that are tagged in general before to be sure that we can visualize them with fluorescence microscopy. And it is important to localize these proteins because it gives information about the function of the organelles. As you can see, the images are really complex, because in the same class you can have variability in shape and in intensity. So the classification is not easy if you are doing feature extraction, handcrafted feature extraction, because it is difficult to find the features that can discriminate this kind of classes. So we proposed also an architecture for that based on a very compact CNN. It is a convolutional neural network based on the mobile version 2. So it is not, it is compact. We don't have a lot of parameters. And we start with the feature extractor layer. But we added, instead of the softmax layer to give the class, we added also a deep embedded clustering combined with the feature extractor to find the class, to predict the class. So it was interesting to integrate the two loss functions, so the weighted sum of cross entropy loss, which is used usually, and with the maximum mean discrepancy loss, because we are looking to clustering this kind of the different classes. So this is why we added this loss function combined with the cross entropy, and you see that we have a gamma here, which is a hyperparameter that we need to tune based on our data. And we tried to see also if we have few data for training, if it is possible to do something. As you can see here, the experiment, we are taking only 20%, 50% or 80% of this data set. This is a public data set used by many people, and it was interesting because we could compare with them our results. So we can see here that what is the impact of this new this new loss that we added, the maximum mean discrepancy. So we did work without this, so you're using only the cross entropy and without augmentation. Data augmentation is very important in medical imaging because we don't have enough data anyway, so you need to do data augmentation. And you can see that without data augmentation, even the baseline is not working well. With augmentation, we have something like this with cross entropy, but by adding this new loss based on the clustering, we get something that is better. So it is something that is interesting, combining the deep clustering with a feature extractor to classify this kind of data. And compared to the others, you can see here with the Inception, ResNet, GoogleNet, and many others that tried to classify these data, so it was done on the same data set. We have something that is really interesting, so it was interesting to use this. It is almost similar with the MobileNet version 1, but we are using something that is more compact, version 2, and we are not doing wavelet decomposition. Maybe the last, very quickly, the last application that I would like to show is for the cerebral microvascular network modeling. So it is very important because this kind of vessels are really those who allows to the brain to get the energy and the nutriment. And you see how it is complex also. This is to show that in medical imaging, we cannot think that we can have the annotation of this kind of data. It is really large network that it is impossible to annotate. And I will show you very few images that we could annotate, but it is difficult to get this annotation, and you cannot ask the specialist to do that for you. What is the problem of that is that we can get some microstrokes that can really very damage your brain. So we can have ischemic brain regions. And until now, it is very difficult to quantify the impact of microstrokes because it is difficult to get these structures with the imaging modalities that we have until now. And why it is important to do that, there are many studies that show that the microinfarcts are associated with high proportion of neurological diseases like Alzheimer or dementia. So it is important to find a way to study this kind of microstrokes and find a way to do this. And until now, we are doing preclinical studies where you need to induce this cognitive decline in the animal models to see how it evolves, and mainly also to see if from that we can have some macro biomarkers, macroscopic biomarkers from these micro structs. Because if it is related to some macroscopic biomarkers, then we can have MRI images of patients and get something about that. So this is why it is really very important to find these biomarkers at the macroscopic level to be sure that we can do that with patients. Because now I will show you some imagings that are done in animal models, but that we cannot use in patients. But even to do that, we need really very, I can say, a complete pipeline for modeling this, because you cannot do this manually. So from this 2-photon microscopy, you need to do segmentation. And this is where a DenseNet fully convolutional network was used. Then you will have to find a way to get the surface for modeling, the graphing, to get the neural net, to get your network. So just to tell you that we did it for a few images for the training set, like you can see here, but it was really it takes a long time to annotate all these microstructures, and it is really laborious, and you cannot ask an expert to do that. It was just to show you that some fields in medical imaging can be very hard to apply classical annotation of the images like in ImageNet. But the accuracy was really good compared to the others. Like here, just if you compare with also the binarization, for sure we'll get something that is interesting. But we had to have the true numbers that took really time to do that. Maybe I will go to, yeah, this is the data set that we use from animal models to find this kind of vessels. As you can see, it is really complex. And at the end, we can compare to the ground truth. We can have something that is really interesting, at least for some cases. But still, to conclude, we have really a problem in the annotation of data in the clinical setup. And we realize also that the state-of-the-art algorithm underperform on new data sets. So we need to have something based on our own data set. As I said, we have a lot of unlabeled and unbalanced classes anyway, because you don't have, for rare diseases, you don't have enough classes. So this is a challenge that you need to consider. The public datasets are not always reliable because it depends who annotated that. And also, in general, they have license restrictions limiting their usage. So we have to find a way to annotate our own dataset. And also, the generalization of the learned models is really a problem. So we need to, as I said, when you take different data from different institutions, you can have different configuration of your system. So it is impossible to generalize very well on new data set. So sometimes you need some metadata to consider to be sure that your model will be able to generalize. So research in this area for medical application is very welcome. In our case, we are investigating also some self-supervised approaches, because this is a way how we can really succeed to have enough labeled data. We need to enhance also the reliability of the algorithm by using the quality scores, and as I said, take into account all the exams that the patient had, so multi-view images that are already taken, we need to use them. Finally, also, we need to focus on interpretable and explainable AI, because for FDA approval, or also for just to be sure that the clinician will accept it, they need to have an explanation of the decision. So you cannot just say this patient is healthy and this one is not. They want to see exactly why the model decided this. So it is very important in medical images. And finally, the collaboration between the two domains, so the AI researchers and the medical specialists, is really essential to be sure that we can together understand and overcome these challenges. So that's it, and I thank you very much for your attention. And this is my team who was behind all this work. And also, for sure, we had this financial support from many organizations. So thank you for your attention.
Okay, first question is why pixel level segmentation is used, not the image level segmentation.
Yeah, very good question. Yeah, indeed, it is easier to say, okay, we annotate at the image level, and it is more easy to get more data annotated with this. The problem with that is that mainly because at the end, when you have to say that there is, like if you go with the ophthalmology, when you say to the doctor, I don't have any sign of retinopathy or diabetic retinopathy, let's say that this decision was negative, then the problem is that we don't know if there is something else that we missed. Is it a problem of edema or glaucoma or something like this? So the clinician will not be, how to say, he will not easily accept the decision if they don't know why this decision. I know that there are many attention models, but until now they are not really perfect. So you can have like the activation map going in elsewhere where you don't have anything. So I understand that if indeed the pixel level is really hard to get because you have to segment all these biomarkers, but in the same time it is a way to be interpretable and explainable. So if you say to the doctor, my model said this because such and such, he will be able to accept the decision and take into account what you are saying. But if it is just at the image level, you will not have this explainability. So this is to be interpretable. The decision is interpretable and because you are doing exactly the same as the doctor is doing. And especially also when you have rare diseases, you will not have anyway enough data to, even if you want to do only image level annotation, you will not have enough. By doing the biomarkers, you don't need a lot of data. This is what we demonstrated. When you have a small set of biomarkers that are well annotated, I can complete with the other images that are annotated at the high level only. And it was the architecture that I showed, the weekly supervised. So combining both will be more interesting to the FDA and the acceptance of the doctors.
Okay, thank you. Same question. Why both the left and the right, the eyes image are used at the same time?
Could you please repeat the question?
Okay, why both the left and the right eyes image are used at the same time for diagnosis, not only left or right or one?
Okay, yeah. Indeed, the one thing is that what we discovered is that the doctors are taking many images. Let's say for one image, they are taking some images centered on the macula, other on the disc, and they are taking into account all this to say if there is something. Now, why the second eye? Indeed, when you don't have enough data, you are trying to have the maximum that you can get. But sometimes also, if you are looking to the progression of the disease, it can be they acquire both images to see if the healthy eye is evolving to something. And it is interesting when you are looking for an early diagnosis. Because if you want to get the early diagnosis of a pathology, you need this longitudinal study and see how the eye is doing. Because when the eye is pathologic, you don't have a lot of choice. There is a treatment that you have to take and that's it. But if you can detect in the other eye when it is progressing, then maybe you can do something more interesting and the patient will be taken in charge for the second eye. But usually, in general, until now, they are just combining both eyes to be sure that they have double of data than just taking one eye.
Okay, last question. Which methods are used for your data augmentation?
Yeah, very good. Yeah, indeed. When you are doing data augmentation for medical imaging, you have to be really careful. You cannot just do rotations or crops or something like this. You need to do some augmentation that can be realistic. Like in the case of, I showed you the atlas that we built for the optical disc. It was very interesting also for data augmentation because since you have what is a normal population, you have the average model, you have the variability of the population also in the healthy population. Then when I'm talking with the variability, it is a standard deviation with respect to the mean model. So what you can do is to add different values of standard deviation around the mean model to get many other data. And you can even have abnormal, because when you augment your standard deviation with respect to the normal, you can get also abnormal patients. So this is a way when you have, I know that many people are using also GANs to do data augmentation to generate synthetic data. But if you have structures where you have an atlas, it is really a very good way to augment your data. The other thing is that the intensity are changing also. You have to see the variation of the intensity on your images using the principal component analysis, and then also vary your vary the intensity on your images. The other thing is the noise, because you will have different level of noise for different configuration. You can add that also and vary the level of noise on your images. So you have to take into account the fact that in medical imaging, it is not the same like in the vision community in general, because we don't have CCD cameras. There are some, but many others are MRI, CT scan, and X-rays, and in this case, the augmentation should not be the same as in the natural scene images.
Okay, thank you. That's all. Okay, finish. No questions.
Good.
Okay, thank you, Frida.
You're welcome.
So thank you, Professor Tang, for chairing the session. And of course, you know, Professor Tang is the general chair of the conference. So we finish today's program, and I thank everyone for attending all these sessions, very interesting papers and applications, and excellent keynote speeches. For tomorrow, we'll have one technical session in the morning, starting at 8 o'clock Montreal time in the morning. Hong Kong time, it will be 8 p.m. at night. We'll talk about medical imaging also, and also data augmentation, as well as forensic texts, and also forensic currency, coins. And we'll also talk about diabetics diagnosis, and also hand vein recognition and analysis. After that, we'll have the awards and promotion of 2022 International Conference, and also approval of the 2024 conference. And we'll have awards to all the sponsors that you've been very kind in supporting the conference. And also, apart from that, there will be a memorable concert. You will see a very majestic, I would say, memorable, stunning performance by the top singers in the world. And the list of singers and the songs are listed under registration on our website. And there will also be a game for guessing who the singer is, so with a prize. So that would be very interesting. And I cannot say any more, but just say it will be spectacular, stunning. So have a nice day, and thank you, and good night to the people in Hong Kong and China, and also good afternoon, people in Europe. Thank you, and see you tomorrow. And Nicola, thanks a lot. Bye-bye.
Bye.